Hey, welcome to today's stream. We're gonna do a long one today. We're gonna try and... Oh wait, is my microphone like super loud now? Huh. Maybe I... like this? Yeah, this should be better, right? Sorry about that. So we're gonna do a long stream today. We are going to do day 14, the advent of code. And if we finish it early enough, we're gonna try and do day 11. We're gonna catch up. So yeah, welcome to today's stream. Now let's get started. I also want to say, well, I'm gonna wait a bit. I have a special birthday wish that was supposed to come yesterday, but it didn't come. And then, so yeah, we're gonna do both of them. And then we are going to take a short break, like between the two. Just so, you know, I have to catch a breather and stuff like that, you know? Gotta take care of yourself. Let me see. Like this. Now we have optimal terminal size. Am I wrong? Alright, let's look at day 14. Also, let me know in chat if there's any audio issues, if there's anything, really. I'm always trying to improve, but it's hard to tell, you know, because I don't watch the stream. I just do the stream. So y'all have to do. Also today, especially, we're using a new encoder. We're using the Intel QuickSync encoding, which is like it has like a specialized chip on the CPU to do video encoding for some reason. I mean, yeah, okay, that's good. So let me know if the quality is bad or not. It should be good. I mean, that's what the online kind of reviews said, but I don't know. I'm not watching the stream. All right, let's get started with today's stream. Let's open up a new one. You're joining us from earlier. You notice that my setup is a bit different, and that's because I am streaming from Iceland now. I'm in quarantine in Iceland. My first test came back negative, so I didn't catch it in Sweden, but I might have caught it on the way. So, and we gotta be careful. We wanna hug or grandmas, right? For Christmas. I had like a super get-up. It was intense. I had like a face shield and everything, but it was nice. All right, let's see. Module main where. Let's look at today's problem. Advent of code 2020. So how's everyone doing? Has anyone done this yet? Does anyone know if it's hard or like what's the dealio? Is it good stuff? Day 14. Oof. Oosh. Okay. Now we're gonna do some stuff. We're gonna be editing memory. Yeah, it's gonna take some state manipulation. Let's see. As your ferry approaches the seaport, the captain asks for your help. Again. The computer system that runs this port isn't compatible with the docking program on the ferry. So the docking... Let me just lower the output of my desktop volume a bit. But if I do like this, yeah, you can still hear it, but it's a lower for me. Alright, because I used to have like a better sound card. I could like tweak how much I hear myself, like the monitoring, and I could tweak how much I heard the audio coming out from my desktop, but now I can't. So, but you know, I think this is quite a nice setup for being on the go, right? It's quite expensive too, but life is not about money. It's about enjoying. So if you gotta spend money to enjoy, that's alright by me. Alright, so let's see. After brief inspection, you discover that the seaport's computer systems are used a strange bit mask system in its initialization program. I'll do you can Although you don't have the correct G-code chip handy, you can emulate it in software. Okay. The initialization program, your partial input, can either update the bit mask or write a value to memory. Okay. Values to memories addressed are both 36-bit unsigned integers. Oof. That's big integers. Good thing we have Haskell integers. Okay, bit mask is always given as a string of 36 bits, written with the most significant bit, representing 2 out of 32, 2 in the power of 35 on the left, and the least significant bit. That is the LS bit on the right. Let me just check one thing. Did I? Yeah. Okay, and one more thing. Just one more thing. Alright, it's okay. So, we take the bit mask. We're gonna use data.bit for this, I think. The current bit mask is applied to the values immediately before they are written to memory. A 0 or 1 overwrites the corresponding bit in the value, while an X leaves a bit in the value unchanged. For example, consider the following program. Mask is a bunch of X's, 1 and then X, X, 0, X. Memory 8 is 11, is 1, 1. Okay, mem of 7 is 101. And then mem of 8 is 0. So the mask it specifies overwrite 2 bits in every written value. The 2's bit is overwritten with 0, and the 64's bit is 60. Okay, yeah, bit representing 64. I get it. Okay, I get it. The program then intends to write the value 11 to memory address 8. By expanding everything out to individual bits, the mask applied is as follows. So value 11. So that's decimal 11. Yeah, okay. 1011. Okay. Well, so it's a decimal 11 there, not 101. Okay. It's applied as the value. So value is 011. Okay, and then it applies the mask, and then it changes this bit here to be 0 and this bit to be 1. Okay. Yes. Okay, memory address 8, and then the program writes to write 101 as 101 to the address 7. This becomes 1, this becomes okay. And like this, and then it has... This time the mask has no effect. Okay, yeah. Finally, the program tries to write 0 to address 8. The value is 0, and then it masks it, and then it's 64. Okay, yeah. 64 is written to address 8 instead, overwriting the value that was there previously. To initialize your Fairy's Doggy program, you need to sum of all values left in memory after initialization program completes. The entire 36-bit address space begins initialized to the value 0 at every address. In the above example, only 2 values in memory are not 0, 101, 101 at address 7 and 64 at address 8. Producing a sum of 165. Okay, seems good. Now let's take in the program and let's get started. New file, test-input. Paste it. Okay, now let's write the parser like we did yesterday. Probably overkill. Let's have a copy of the input here. Okay, we are going to import text.parsec. We're going to import text.parsec. This is going to be like this. Main. So how we're going to represent the program, we're going to say data memory, data memory equals, okay, so the mask, so the the mask is going to be a function from bit to bit, right? Import qualified data.bit. let's just import data.bit, right? So we're going to be using integers here to represent these values. So this is just going to be integer to integer. That's a function, right? Okay, and then the memory is going to be an array with integer indexes because we have too many bits to carry around an int. Memory is gonna go from integers to integers. Okay, what doesn't want data.bit? What? Data.bits, like this. Now, get input file path to IO memory. Get input equals, so parse right, we have to import text.parsec.bytestring what is that? Is this overwritten? Oh right, we have to import data.array like this. Okay, how's everyone doing tonight? Oh hey Timmy. Yeah, happy birthday yesterday, Timmy. Well deserved birthday. Parse file. No, wait. What was the text.parsec one? Text parsec. It's quiet today. It's not as many people as usual. I think it's because it's a Monday. People don't like Mondays. Parse from file. Parse mem. This is gonna be parse from file, parse mem, IO. So this is gonna be do res fp and then is of can't we just like use something from data.either to do this? Yeah, I know, that's why we need state. So we're gonna be using the stmonad. Oh, set the mask multiple times. Okay, I see. So every instruction will set it multiple times. Okay, I think that's maybe spoiler alert for part 2, right, Timmy? So parse mem is going to be a parser for memory. Right, the actual input will set the mask multiple times. Okay, so I see. So we will need to do it that way. After brief, okay, so the initialization can either update the bed mask or so we have an instruction here. So let's see. Data instruction. It's going to be it's either a mask update. Take care. Or it's going to be a memory mem op, and we're gonna have the index of the mem op, and we're going to have the value of the mem op. Let's deriving show. So this is going to be a list of instructions. Okay, so parse So parse ins. That's just gonna be set by new line of text dot parsec. Yeah, I would use our auto parsec here, but it's not installed by default on my system. So I'm trying to use like things that are there by default, essentially. Let's see. That is going to be set by 1. Right, and it was here parse ins and then a new line, right? Parse in and then so parse ins is going to be a parse ins parser for okay, so we parse in, and when we parse in, that is going to be okay, so it's going to be a choice of parse a mask or parse mem up. Now parse mask. So what is parse mask going to be? Parse mask is going to be. It's going to be, I think, let's just do. So it's going to be do. So it's going to be string. So that starts with a mask. Mask space equals space. Okay, and then we will have a parser. Yeah, I mean, I'm not gonna download the input right away. So let's see. But I believe you. I believe you, Timmy. So how do I define a mask? Did it out in bits. Let's see. Bitwise or so. So we're just gonna parse them. So they're gonna be X or 1 or 0. So we're gonna have like a list of nothings, or it's gonna be maybe and then just 1 or just 0. I think, or no, or just nothing, just true or just false. Okay, so we're gonna do many 1. Res is many 1 of parse mask info, something like that. So parse mask info. So then we're gonna like return a mask info. So now let's just do here mask info to mask over this. Now parse mask info is gonna parse. It's gonna parse maybe bool. It's gonna be a parser for maybe bool. Parse mask info is gonna be. It's going to be what is it gonna be? It's gonna be so choice of, okay, it's gonna be char x, and then we learned yet last time like it's this operator, right? What was it? It was that operator, right? Yeah. So then we do nothing and then this. Let's see. Okay, and then we will say nothing char x, or just true char 1, or just false char 0. Okay, and now we have to define mask info to mask. It's going to take a maybe bool and it's going to return an instruction. So, and we're going to define a mask. Okay, it's from integer to integer. Okay, so we're going to say here mask info to mask. Oh no, this is like per instruction, right? No, yeah. So we will take in a mask info to mask. That's gonna take a list of maybe rules to instruction, right? So we are going to say zip. So it's gonna take, you know, 0 and so on. And we're gonna look at the reverse. Mask, so reverse of the mask. Okay, and we are going to say so where. Okay, so now, so we're gonna, and then we're gonna apply this f function here. We're gonna apply, what's the type of uncurry again? Let me see. Uncurry. Right. We're gonna apply a map uncurry f to this, where uncurry f no, this is, we're not gonna define uncurry. We're gonna say, so f of I comma, so f of I comma nothing, that's going to be id. I want to see, so because like now I'm like defining a function, we'll just like apply all the functions in a mask to the integer, but that seems a bit much, right? Mask. Okay, let's just do it this way. This, so if it's nothing, and it's gonna be a function, so we're gonna be getting a list of functions, right? This is just gonna be, okay, so we're gonna first, before we do this, we're just gonna say filter wait, let me see. So we have these. What I'm gonna do first is I want to like do cat maybes and then just let me see. I sip with numbers. Cat maybe of So we're gonna say here drop nothing is going to be, so I comma nothing is gonna be nothing. Drop nothing of I comma just x is gonna be just I comma x. So then we're gonna zip this, and then we're gonna cat maybe of map drop nothing of these, and then we're going to map. Okay, let's just look at, yeah. So this is gonna be giving us like the list of instructions, and then we will say now, and then we will have like a list of, you know, 1 is gonna be true, 2 is gonna be false, or like 5 is gonna be false. So then we want to say, so to fun is going to be to fun I comma true. Okay, so to fun I comma b is going to be if b then set bit. We're gonna flip set bit I, else flip. Let's see here. Let's see. It's gonna flip, and then if b then set bit, else clear bit I. So then we change them all to functions, and then we are going to say map to fun of this, and then we're going to say fold L1 okay, now fold L, and we're gonna fold L with compose on id of this list. Do you get what I am doing here? It's kind of crazy, right? Anyway, this is how I'm going to do it. This is going to be very inefficient because we're not using the bit operations. We're using data.bit, and I don't think that it does any optimization of it. But that's how we're gonna do it. I'm just wondering because like it doesn't say any. Oh, here, ask. Oh, this is gonna be mask. Okay, because it's not. It wasn't returning any errors or anything. Let me see. Parser on input like this. Okay, and the issue here, couldn't match expected typing instruction. Yeah, so this is gonna be mask of cat, and there's gonna be cat maybes. We're gonna import that from data.maybe. Okay, and oh wait, no, yeah, wait, we can just do map maybe, which is gonna be fine. We can map maybes here. Okay, mask info to mask MSK. Let's not derive show. Let's actually say instance show instruction. Where? Because we can't derive it. Show mask MSK is equal to show mask applied to 0 bits. Show mem up n equals. So this is gonna be mask equals plus. It's gonna be mem plus I show I plus. This equals plus n show n, right? Okay, so this is gonna be parse ins. Parse ins. Okay, now we parsed masks and we did this funky integer thing. Let's parse memory operations. Parse mem op. That's gonna be easier, right? Parser instruction. Parse mem op. That's gonna be do, and then it's gonna say mem. So it's gonna be string mem, and then it's gonna be by separated and ended by sep. Oh, okay. Why is it? I wanna take like a. I wanna take many till. Okay, many till, right? Then we're gonna say adder is gonna be many till. Applies parser p. Okay, many till, and then something here, and it's gonna be char like this. Returns a list of values returned by p. What does try mean? Try. I mean, it's okay. So we want no. Okay, yeah. So we want to say try this, and here we want to say many till digit, right? And then we want to say we're gonna, you know, just gonna read this. And then, so that's gonna be our address, and then it's going to say string. I think it's gonna say like this. Like, I think it will have consumed the char. And then string, and then val is gonna be the same again. That's gonna be read many till new line many till digit new line, and then we're going to return mem op adder val. Doesn't Parsec have a handy decimal parser? That might be. That's actually a good idea. Yeah, well, no, it parses digit. Parsec decimal. So this is like not included in Parsec, right? So we'll just read it. It's gonna be fun. Okay, now let's try and see what happens. Main, it's gonna be print main equals do get input test input into print, but we haven't defined get input. What's wrong here? Oh yeah, okay. Ding, 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 ding. We're gonna get a parser for sure, right? Or did we just nail it? Oh, right, we have to run it. Okay, we got mask 64. But we didn't get... we didn't get anything else. Probably because... this one failed? No. So we are showing it here. Oh, okay, so I think it's just gonna be not new line. I think it's gonna be just many one digit. I think because we did set by on the lines, right? Huh. Maybe we do this and then not this. Okay. So we did a choice to say parse mask is string mask equals, okay, mask info to mask many one parse mask info. Yeah. We don't need the I here. So this is gonna be what, mem 8, yeah, space equals space. Ding 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 ding. Parsec has some kind of thing, right? Can I just write memo to make it print out what is happening? Huh. Let's see what happens if I say here. So there we get mask, and then what's left? Oh, okay. Oh, right. It's because this is Windows. So it's not actually new line, it's gonna be end of line. God damn it. Okay, see? This is why Parsec is nice. Are you out of town? Yeah, I'm in Iceland. I'll be here for Christmas. I'm currently just quarantining. Which is, I mean, that's fine, right? Unexpected E, expecting mask. Okay, they exit. Okay, now, so now it wrote mask. Oh, it's still doing that, right? It's still like showing me that the entire state here. Is that just because it will always show the entire state? Unexpected E, expecting mask. Put try in front of parse. What? Really? Because like in text.read and in text. And in text dot and in arrow parsec, like I used arrow parsec and then I didn't have to, I could just say choice. That's lame. Yeah, but okay, yeah, makes sense. So it had already kind of tried to consume mask. That's weird. Thanks, Etop Uzov. You know, hacker nicknames or like online nicknames, they weren't really designed to be pronounced, you know? They're designed to be looked at. So they always become a bit weird. Alright, now let's stop this trace here. We don't need it anymore. Okay. Now we have a list of instructions. It's Alex. Hey, Alex. Yeah, exactly. So my name, like Treatlow. It's always so weird when people are Treatlow. I'm like, you know, it's not supposed to be said. Okay, now then we have the memory, data memory. It's gonna be mem, and then this is gonna be like the current memory. Okay, so we're always gonna apply the current. Wow, cute name. It's supposed to sound hard, you know? It's supposed to be like, oh shit, Tritlo is here, he's gonna take over our systems. Why use array and not map? I think it works both ways. Because I don't think the array is just kind of optimized for enumerables. I think it will be faster, but I don't know. It's just because it's an array, right? It's a memory, and we're gonna be addressing locations in memory. That's why I want to use memory here. So let's see. Run instruction. Instruction to memory. So we are going to say this is actually going to take memory and then an instruction and then a memory. Okay, run instruction mask f is going to be, and then the m is going to be what is, we called it mask, right? We just call it mask. Let's see. Yeah, we called it mask and mem. Let's move this below. So this is gonna be m, and then it's just gonna be mask equals f. Oh, thanks for the follow, Sicilian salad. Wouldn't mind some Italian salad right now. Like, you know, the Italians, they know how to make salad. They just put like a bunch of like feta, okay, not feta cheese. Anyway, like the salad I imagine is like you have like balsamico. Balsamico is so good. You can hear it. I've been in Iceland for a couple of days now, and my Icelandic accent is already coming out. That's just how it is. Okay, run instruction mem up. Okay, we're gonna take the memory m, and we're gonna say mask equals mask, and we're gonna say mem up adder val equals. First of all, we're gonna apply the mask to val, and then we are going to update array. Array. Also, Timmy, so we might try to do it more optimally later. Let's actually just do this right now. Let's say here, instead of saying this, let's say here that we're gonna say run program. It's gonna take in a list of instructions, and it's gonna be an st data.st data.array.st st monad Haskell monad st control monad st, because I think it's gonna be super slow if you don't have that. Import control.monad.st. Import data.array.st array. Data.array.st. So we're gonna have here run program instruction. How do we write this again? So this is gonna be the state. The S is gonna be the state, and then the A is a return. So it's gonna be, this is gonna be the mask. Integer to integer, and it's gonna be our st array of integers to integers. That's right. So that's not how I use st, right? Okay, so we actually want to do this run st array. That's the thing what we want to do. So is it gonna be, because I can never remember this. So run program. So run program is just going to take in a list of instructions, and it's going to return an array of integer. We don't care about the final mask, right? Program instrs equals do. So now we're going to say where run program prime equals run st array. Google, let's see, stu array. Can integers be unboxed? Probably. I mean, yeah, that's what I'm thinking, right? So let's see, run stu array, unboxed array should be an instance of x int 64. Beep, beep, beep. Yeah, okay, so let's do that. Run stu array. So let's have these not be data.integer, let's have them be data.int64 and 64. And then these are going to be x64 or 64 to int64. And define. We need to import int.int64 from somewhere. We're not using this anymore. Whereas int64 defined, it's defined in data.int. Import data.int. Okay, so now we have 64s to 64s. Like, the cool thing about that is the way we do the mask info thing is that it's using data.bit, so that's gonna be okay. It's still gonna work. So run stu array $do. So it always starts with an initial mask, right? Bitmask is always written with the most. Bitmask goal union unless the current bitmask is applied to values. The program starts. This program starts. Okay, so what is the default mask? Let's see. Can either update. Let's just get the input. Okay, yeah, it always starts with a mask. Let's see. This is day 13. Okay. So this is going to be run stu array, and this is just going to be something that is going to return us a run stu array. It's going to return us a u array. Then we need data.array.unboxed. Okay, so run stu array. So we want to write like a loop in the thing, right? Okay, so this is gonna be for all s sts so we're gonna write a loop somehow. Wait, so let's like this is gonna be initialized here. So this is gonna start with mask, okay, and that's gonna be mask f. So we're gonna say msk is gonna be new stref Google new stref. That's in data.stref. Import data.stref. New stref msk msref. And it's complaining, so okay, it's gonna be this. And then okay, let me see. Safe way to create and work with unboxed mutable array before returning an immutable array for a proposal. This function avoids copying the array before returning it. It uses unsafe array freeze internally, but this wrapper is a safe interface to that function. Okay, so let's see that. So we want to create like a new st array somehow. Oof. So now we need m array, right? Yeah. Okay. Import data.array.m_array. Not that safe. Okay, and then so mem it's going to be the new array. I don't think creating a new array with the bound 0 to max bound of int 64 is a good idea. I think Tim's idea of using a map is better. Because it's gonna be super sparse. So let's do that instead. let's just write it like this. I think it's gonna be fine. I think it's gonna be fine actually. Map int 64 to int 64. No MRAs for us. Import okay, so let's see. We're gonna say so this memory here. Okay, so the M and the mask with the mask is equal to mask, and mem equals to mem. So then we're gonna say what is it complaining about? I need a record wildcards. So I need to do something like this, right? Oh, let's do it like this. But and then I need yeah, this is gonna be a mem. Yeah, exactly. M at mem like this. And now I need to enable record wildcards. Wow, see that editor stuff? Yeah, Timmy got it also. This is gonna be the problem here is that, yeah, so we didn't change the types here. Okay, so this is going to be, so we have the memory. This is going to be M. We don't update the mask, but the memory is going to be, we're gonna do like data.map.modify or something. Data.map.modify modify with something like that. Or no, we're not even gonna modify with, we're just gonna say insert. So this is gonna be map.insert address mask val mem, like that. I'll even do it like this. Run program. Taking a list of instructions. It's gonna return as memory. Data initial memory. No, it's gonna be initial memory. So memory initial memory. Let's call it mem. Equals mem. The mask is just gonna be mask equals id. Mem equals map.empty. Run program. Run program equals fold L1. Okay. Fold L. Run instruction. Initial memory. Let's see what happens. Test input print.run program. Yeah, that's because we have here... We had a nice show class here, right? Let's write this like this. Show mask MSK equals show okay, show mask, we have that. This is gonna, so we're gonna say instance show memory where show mem equals show mask plus new line plus show mem. Let's see what happens for the test input. Problem is 7, 101, 8, 64, and I think that's exactly the result. So we do the sum here, and yeah, okay. Solution. List of instructions to an int 64. Solution is going to be so where res equals run. So we're gonna say, so this is gonna be, we're gonna run the program. Okay, and then on the result of that, we're going to access the memory. And then we're gonna say, we're gonna get the elements of memory. We're gonna sum them. Map.elements. Print solution. Alright, that works. Let's see if it works for our input, or like how slow it is. Because these mask stuff, that is not a fast way to do it. Let's see here. Measure command expression day 14 out default takes 45 milliseconds to run it. That is a bit much, right? Let's see. All right, we got the first one. Beautiful. Now, let's see how long we're gonna stay today. For some reason, it must be using version 2 of the decoder chip. Instead, it acts as a memory address decoder. Immediately before a value is written to memory, each bit in the bit mask modifies the corresponding bit of the destination memory address. Ugh. If the bitmask bit is 0, the corresponding memory address bit is unchanged. If it is 1, it's overwritten with 1. A floating bit is not connected to anything and instead fluctuates in particularly place practice. Oh my god. What? Yeah. Can you imagine? You know, like, you know, we're, I mean, I assume like we have a lot of computer scientists watching this stream and you're gonna be like, you know, the fairy guy would be like, is there a doctor on board? And you know, you got all these medicine doctors and they're gonna be like, I'm a doctor. And they're gonna be like, no, we need a doctor of computer science. Why? because there's floating bits in our decoder chip and we need someone to fix it before it's too late. And I would be like, you know, I've been preparing for this moment my whole life. That'll be good. Okay, so now we're gonna need to change our... Oh my god, what is this? Version 2 decoder doesn't modify. So okay, so if the bit mask bit is 0, so okay, it doesn't change 0. That is okay. If the bit was 1, else it's floating. A floating bit is not connected to anything and instead fluctuates unpredictably. In practice, this means that the floating bits will take on all possible values, causing memory addresses to be written all at once. When this program goes to write the memory address 42, it first applies the bit mask. Resolved. And then the 4 bits are written, 3 of which are different and 2 of which are floating. Floating bits take on every possible combination of values. With 2 floating bits, 4 actual memory addresses are written. Sheet. Hi, Cracks. Nice to see more people. We just solved part 1, we're solving part 2. It, like, you know, because I'm not getting oh, here's a nice way to do this. I mean, unless we had like a quantum computer. Because I'm just thinking, like, won't we just have to simulate it? This is the advent of code, like the code advent calendar, and we're solving all the problems. We're on day 14. We solved part 1, and now we're gonna try and solve that, part 2, and then we're gonna move on to day 11, because yeah, I was traveling, so we didn't finish that. Okay, floating bits take on every possible combination of values. With 2 floating bits, 4 actual memory addresses are written. Next, the program is about to write memory address 26 with different bit mask. Oosh. So, okay, yeah, but the program is about saving the ferry that Santa is on from crashing. Okay, the entire is still being initialized to the value 0 at every address, and you still need the sum of all values left in memory at the end of the program. Okay, we're not gonna be doing this with a map. Okay, what we're gonna be doing is we're gonna be taking every single memory address. We're gonna be mapping the masks to them. And we are gonna try and figure out, like, the last modification to it. I think that's something, right? Because, like, these floating bits, like, they will clash. They will clash in some way. You know, because we're not good at bit manipulation. I mean, so I think we could brute force this, but it's too much, right? Let's see, the input is the same, right? Let's look at our input. Yeah, you see this is like 575 lines of code, right? And oh, sweet. Let me just reply to one message. Alright. You look like Monkey. Who is Monkey? Your voice audio is behind, by the way. Oh. That is... Let me do one thing. One thing only. Thanks for noticing. Yeah, because I can delay it. I can say render delay, and I can say, let's see, is it 10 milliseconds? 15 milliseconds. Is it better now? Chris? Cracks? Like, does it match my voice? I didn't notice this in the video I took. So is it okay? Let's do binary search. It's a bit better, but it's still like it's still behind, right? Let's put it up to 25. How's that? I can do better. Yeah, I mean, that's what I'm saying, Timmy. I mean, that's like, that will work. But, that's like something we don't want to do. Okay, let's begin by, this is Haskell, my favorite programming language, and many others' favorite programming language as well. Let's see. Let's see what happens. Let's collect. So I think what we want to do, we want to collect all the masks, and so kind of like for each mask. What are they gonna be turning out to be? Yeah, let's see. I mean, on the test input, this is gonna be terrible, right? Like, literally gonna write into every single address. Okay, now, first of all... Oh no, we can't deduplicate. Let's see, can we deduplicate in the input? Like, is it often writing to the same thing again and again? Doesn't look like it. So let's think about it. Yeah, this is Haskell. That's what I just said, right? The Haskell programming language. Quite a nice language. Like this is not a language, this is just the input we have for our problem. But this is the language itself. Okay, let's think about this. So the amount of x's, the amount of x is in the address will tell us how many times. So here we have, like, if we have 1x, that's gonna be repeated 2 times. So we have 2 x's, it's gonna be repeated 4 times because there are 4 possible values. So it's gonna be, it's gonna be like that, right? 2 to the power of number of x's in the mask. How many tabs have you opened? I don't know, man. I lost count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. That's how many tabs I'm on right now. Okay, so let's count the number of x's in a mask. So let's look. So cause like we count a number of x's in a mask, So the thing we have to be careful is about clashes. Because you see what I mean to me, right? So this is gonna repeat 100 4 times in memory, and this is gonna repeat 1 8 times in memory. So the result is gonna be 4 times 100 plus 8 times 1, which is 408. Okay, but the issue is that some of them are... This will return right to 8 addresses, but some of the issue will be that, you know, some of these addresses will clash. That's the key trick. Let's look at it. So this will not be this anymore. Not just the mask function. It's gonna be the actual mask. It's gonna be actual string. I'm just gonna call it string. And then here we're gonna pass mask, and we're gonna say msgr is gonna be many1 like this, and then it's gonna be msgr mask in for the mask, msdr instruction, and this is gonna be mask of this comma mask. So okay, so this is actually gonna be not a string. It's gonna be a list of maybe bool. Let's see, and it doesn't like something here. Yeah. Okay, right. So for solution 1, this is gonna be so run instruction mask f f comma x is gonna be fx. Let's just not do it this way. I think we should just kind of start over for part 2. Because it's just kind of completely different stuff we're going to be doing. Okay, get input 2. So these are going to be... let's actually not do it like this. Let's just start a new file called day 14 part2.hs. Oops. Let's copy and paste it. Rename it to day 14 part 2. Okay, so now the mask is gonna be oh, nice. Always good to have little brothers to do that. Okay, let me have some candy. It's good stuff. Yeah, I know Watch Dogs. I never played it actually. It's like too much of a AAA game. Meaning, because like I usually, like I have laptops and like, you know, computers optimized for kind of running code, and that usually doesn't include such a good GPU. So I have a hard time playing all these nice fancy games. That's it. How do you figure out which ones are overlapping? It's a real question here. Okay, so if you're just joining us, we're doing part 2, the advent of code. We know that we could just emulate it and just run it, and we'd probably run like not slow, a couple of milliseconds, or you know, less than a second. But it's Turkish pepper. The thing is that my dad doesn't eat candy, so he sometimes just leaves like random bags of candy on my desk, right? Problem is that I don't live here anymore. I don't really like Turkish pepper either, but now I have a bag of it on my desk. Like, you know, you remember the perubrödsökur, like the Icelandic candies? That was the best. In Turkish, this is almost like that, except they have like a pepper core. Well, I'm like, you know, why you like this? Okay. Oof. Oh, nice. Sure. I mean, just leave the link. I'm not gonna play it right now. But yeah, if you leave the link and I'll catch up on it after the stream. It's the hard part about programming, you know? When you're like, you know what you kind of want to do, but you're really trying to figure it out. Yeah, I will. I will. Let's see. So we will get 4 times whatever it inputs into that memory. But then we need to figure out how many times will it clash. So can we like reverse engineer? Like go in the opposite direction? But then like we have to add all the keys to a set. Can we like take a mask and check if an address is covered by it? Because that will depend on the addresses too, right? Okay, let's flip it and reverse it. Yo, boy. I wish I could play more songs here. I can only play these lo-fi things from this guy, Harris Heller, because it's like copyright-free music. So I actually have like a. So, what do you guys want to listen to? Stream beats, EDM, lo-fi, or synthwave, or hip-hop? That's the options we have. Because now we're gonna engage thought mode. We're gonna go EDM. We have to think. All right. Like, if I was just programming... Oh no, I shut it off. If I was just programming right now regularly, I would like blast some Rihanna right now. I love like 2009, 2010-ish pop dance music. I have the worst taste in music, but you know, I'm proud of it. I like it. Good stuff. Wow, Dylan Beetle is rating with a party of 4. Welcome, party. Hope you enjoy the show. It's mostly me thinking about what I'm trying to do here. And what I'm thinking is, so the thing is here, right? This address here, we have this address here, right? Or this mask, okay? I'm like thinking, you know, we can... Yeah. So, I mean, we know we could just simulate it, right? But we're trying to like reverse engineer it to get like an O event solution. The thought is, you know, we could like walk backwards in the input. But look at this mask. What are we thinking? If the bitmask bit is 1, the corresponding memory address bit is overwritten with 1. So so if anything is covered by this one, covered in the sense that these X's. So I said I would do a marathon stream today, right? And I would like finish this day's and day 11. I don't think we're gonna get to day 11. This is a hard problem. You want to do it properly, right? So only these bits will matter. The zeros. Because the other bits, the ones and X, not the X's and O's, the ones and X's. Yeah, so the problem statement here is we have a mask, then we have a memory address, and we're gonna write to this memory address according this value according to the mask. But we have these floating things, so that like the X's, they take everything and they change them up. So that's gonna be it's gonna be a mess. Well, let's consider here. Test input. So let's just make test input part 2. Test input 2. And it's gonna be here. Okay. Now, let's look at this. So, 42 is equal to and we have 26. Let's just copy. Oh my god. So the thing is that this isn't quite as good as the input, in the sense that so here we have the mask, right? And if this were 1, like, it will always be turned into 1 below. So the only bits we have to look at in the addresses, what is the what is this? It's supposed to be 1. I forgot to say that here. No, it's there. Okay, so also into the power of 264 is not going to be. No, okay, it might be. No, it's not gonna. It's gonna be big. Let's see. I'm gonna go grab some water. So the idea is that, okay, if the mask has a 1 in it, so then and then we don't need to look at that bit. So how can we optimize that? Icelandic water is best water. Okay. Let me see. So we walk backwards. Now I have to stop you. You don't like Icelandic water? Wow. You know, there's a reason we all left Norway to live on an island in the middle of nowhere. And that's mostly the water, you know. I mean, some people say it had to do with taxes, but I think it was actually the water. I prefer Icelandic water to the Norwegian one, actually. I lived in Norway for like 2 years. And yeah, I just like my, you know, because so there's a saying in Icelandic which translates to, you know, never was Iceland loved as much, or nowhere was Iceland loved as much as in Copenhagen, right? Like when the students went to Copenhagen to study, that's when they started loving Iceland, right? So the thing is, like, because I live in Sweden now, I lived there for 5 years, and I'm like, I miss Iceland, right? So everything from Iceland is the best. Okay, so we're gonna be walking backwards through the program. We're gonna be figuring out the space of that the space each mask covers. Okay, and then we only so like for the first part we add all of them like as many times as the number of x's in the number, and then we go up. Let me see. Let's see. So first let's actually, so we will parse it, but we were gonna parse mask as just many one. Okay, so this is in the part 2, so we're just gonna be modifying stuff here. This is gonna be a list of maybe show. So this is just gonna be, we're gonna be deriving. Do not drink and derive. So we're gonna be deriving this. Try parse mask. Mask many one. Okay, this is gonna be, and now this is gonna be mask. Parse many one, parse mask info. Yeah, this is just gonna be many one, parse mask info. Parse memop, that's gonna be the same. Yeah. So parse in, try parse memop. Memop. This is because this is gonna be a parsing mask equals, and then it's gonna be mask over this. Okay, and now let's look at them. We're gonna remove all of this. This is no longer relevant. test input 2, and we're just gonna print it. Okay, let's see. Oh, this is the wrong one. Day 14, part 2. Got an exe. Okay, we have the masks and then we have the memops. Yeah. I mean, you're probably from the north, right? I think that's why you think the water in the north is good. I was raised in Reykjavik water, you know? It's my birth water. So this is... Okay, so let's parse these into blocks. So what is a block? A block is gonna be... Data block is gonna be... a block, and it's gonna have a mask, which is gonna be a maybe bool, and it's going to have memops instruction. This is just gonna be a list of pairs. 64, comma in 64. Then we write deriving show. Wow, you can't shower in Reykjavik? I for one love it when my skin gets torn off by the sulfuric acid. Nothing wakes you up like some sulfuric acid in your shower, you know? List of instructions to a list of block. 2 blocks is going to be a we've written the split add function before. Let's just grab it. No, not here. That's before I used parsers, you know? I was doing these split adds. When did I do it? Split when? Alright. We're gonna copy paste split when? They should really be in the standard library, but you know. 2 blocks is going to be split when his mask. Oh no, and now we want the mask. So this is gonna be X. No, damn it. We're gonna be essentially, okay, we're gonna rewrite split when. So let's see here. Where is mask? Mask of anything equals true. Is mask of something else is false. So we're gonna say ins. This is gonna be like case break is mask of. So this is gonna return us. Ooh, do. So this is gonna be, first one is always gonna be a mask. MSK appended to a list of instructions. So, and then we're gonna say case break is mask ins of first comma rest. That's gonna be block block MSK first. So here we're gonna say to pair mem op b equals a comma b, and we're gonna so to pair of anything else is just an error not applied to mem op. So we're gonna take the first and then we're gonna take the rest, and we're gonna say map to pair of the first, and this is gonna be concatenated to 2 blocks of the rest. First, and if we don't have anything here, no, this is just, it's gonna be like this actually. Where, so we're not even gonna say here. We're just gonna say like this. And then we're gonna say this applied to the rest. And it's gonna be 2 blocks of an empty list is gonna be the empty list. So let's look at this. Yeah, the swimming pools are legit. But I don't want to go to swimming pools right now. I'm also in quarantine. It's literally illegal for me to go to a swimming pool right now. So now we have the blocks. Now let's reverse the blocks. Okay, so now the first block. So what was it? So nothing was X. Gee, no, I moved my keyboard. Screwing up my entire setup here. Let's see. So I'm looking at this. But we still have to figure out the... In previous days, the input has been designed such that there's more specialized... Are we sure that there will be an address clashing here? No, we're not actually sure. You wanna test it? That would be funny, right? Okay, let's just do that. Block. So block sum. That's gonna take. That's gonna take. Oh, this is blocks. Turns it into 64. Returns an integer actually. Let's just do an integer here. Block sum of let's just do it for one block and then we just sum up for all of them. So it's just gonna be a block where so nothing equals length of the mask minus length length filter filter is just because I don't want to define is nothing. So we're gonna say num nothing times. So we're gonna write the memory operation to memory. Let's dedupe the memory operations. Do we have a nub by? Yeah. Deduped equals nub by compare. So it's gonna be equal on second. No, on first. Dot function of on. So we're gonna dedupe num by first on a memops. So this is gonna be a num nothing. No, it's gonna be 2 to the power of num nothing times sum $map S&D deduped. And this doesn't work because okay. Oh, this needs to be imported. Import data.list. And let's see. Problem here is that this is not an integer, right? Now this says could match will type integer with you say will there be address clashes, and I think there will be, right? Because we got, that was from the first problem, right? We got 408. Yeah, exactly. There's lots of clashes, so let's grab the mask function here. Okay, we don't have to grab it. These people, they're always trying to make me become famous. I don't get it. Okay, we've nubbed the memops. Can we just like have a set of addresses which are not covered, because we don't like we don't have to simulate everything. But let's just do the kind of the weak thing and grab the covered thing. No, we need to figure out which ones are. I don't need these. Yeah, there are a bunch of clashes, right? I mean, we already we saw it from the test input, right? That's why it doesn't sum up to 408. Because these are already covered. So I used to be a Linux user, but then I turned to Windows because my work machine has Windows and I couldn't do a boot. And I just kind of learned how to use it. But I've been using VSL2 a lot on my other computer, but like I'm not allowed to update this one to the like Windows 2004 or like the version Windows 10 version 2004, which allows me to use proper VSL2. So while I'm waiting for that, I'm just using PowerShell. But on my home computer, which I have full update rights for, that's where I can do it there, right? Let's see. I'm not gonna simulate it by running the instructions, but I'm going to do something similar. So let's see here. You go to update, check for updates, and you know, you click this button and it will say that you can update if your organization allows for it. But yeah, it just says up to date and it's like managed by organization, so I can't fix it. I press a Windows key and just search for update. Check for updates. Keep your machine up to date. It's important stuff, you know? Addresses equals map first. Memops, we're gonna have, yeah, import data.set. Maybe, you know, maybe there's like a nice way to do it, but not for me. Set.from list. addresses set from bottom list. Well, thank for the follow. X message. I bet X message is a Linux user. Oh, sweet. Okay. Yeah, I mean, I managed to do it on my other laptop or my other computer, but it was illegal. Or like, you know, I'm not allowed to change that setting on this machine, which is very annoying, frankly. Okay, mask to addresses. It's going to take in the maybe list of maybe bool. Turn into a function in 64 to set in 64. Okay, so the floating bits, so the zip 0 dot dot reverse mask. Okay, so map. Okay, so and then we're gonna say here where have of a pair of I comma. So if I have nothing, then it's an X. Okay, if I have 0, it's gonna be ID. That doesn't. So if that is unchanged, F is equal to I comma just true, then it was 1. No, this was just false. Just true was gonna be flip set bit I. This is gonna be set dot singleton of what is it saying here? Oh. So let's just first apply the the ones that just set it, right? That will update the number. So let's see. So this will give us a function from int64 to int64. So the func will be func takes in I64 and it will say, okay, zip 0 on the reverse MSK. We will just id, and this is gonna be just id. This is gonna be, and then we're gonna map maybe f. Okay, so where base equals base I64. So first we apply the base function to get the actual function that we're going to be looking at. Fold L period dollar of id dollar. So then we have the number, and now we have to look at the changes we're gonna make. Yeah. Right. So this is gonna be first num to work with equals, it's gonna be base I64. So that's the number we're working with, and then we're gonna be flipping the bits. So here we will have x locks is gonna be map fst of filter not is just of the so we're gonna take the second not is just map first second of the mask, and no, this is the mask. Yeah, so this is gonna be mask ints mask ints. Now, for each of those indices, we want to create the set of numbers that it generates. Oof, this is going to be exponential, right? And for the numbers x. What music playlist are you listening to? This is Harris Heller's Stream Beats EDM music. It's on Spotify, and because like Twitch has been doing a lot of DMCAs recently, apparently, and I don't want to be hit by one. And also, like this is like, you know, it's okay. So he has this playlist called Stream Beats EDM, copyright free electronic music, and then, you know, my also. You know, my YouTube videos of these sessions are also like, they're not taken down by DMCAs and stuff. Okay, so I will generate. Okay, so xlocks. Up the x loc is gonna be so empty, and then so far is gonna be so far. Up the x loc I so far I, and then is. That's gonna be a map set.map set bit flip set bit I of so far. And so up the X loc is gonna take in a list of ints, and it's gonna take a list of set int 64, and it's going to return int set int 64, and this is going to be set.union, and then we're going to clear the bit. Clear bit. Oh my god. No, I'm doing the thing again where I press the wrong button. And yeah, this is supposed to be so far. This is gonna be func of this is just doesn't need to be in the function itself. This does not need to be in the function itself. Oh yeah, no, this all has to be here. So this is gonna be up the X loc of the X locs of set.singleton num to work with. And this is going to be func. Okay. So data block process. Okay, let's see. So here we generate all the addresses. So for each address we generate the addresses it can go to. Let's see. So this is going to take in a block, and it's going to take in a set int 64 integer, and it's going to return set int 64 and an integer. Okay, let's look at this first, right? Oh no, let's do it. Let's just do it. Just roll with it. Set int 64, comma integer to set int 64, comma integer. What is it going to do? So we're going to take a covered, and we're going to take the cur sum. So we are going to say okay, so adder func is going to be mask to addresses of the mask. And you find, so that's the address function. Okay, if anyone here is Game of Thrones, Theon Greyjoy and Tyrion. Damn. I have no comment. But that's a bit funny, right? So, we're not gonna be using this. We're gonna be using deduped. So we're gonna say here fold L prime add and update init and then deduped. Where, oh wow, thanks for the follow. That was nice. Add and update. That's gonna take the covered and the current sum, and it's going to take in an address and a value. We're going to say, okay, so okay, where address equals adder func address set of the address, but we are going to say, oops, we're gonna say set dot difference. So this is gonna be, yeah, so this is gonna be set dot difference without covered for nested where clause. Yeah, I mean, this is, we're scoping things here, right? So we're going to add and then new set. So total val added is the length of adders times val. New so covered prime is going to be covered, oh, can I say like disjoint union, and that's faster? Disjoint union, no, okay, that's calculating it. Okay, this is the same union. This check is subset of. No, I'll just say union. Covered set dot union of the address. So it's gonna be cur sum plus total val added. No, this is gonna be covered prime, and this here is address set. Now it's complaining that the return here is wrong. Yeah, so we can't fold this here. So let's flip this around. No, we don't need to flip it actually. This is gonna be a print of fold L prime of flip block sum on the initial value is set dot empty comma 0 let's see. Non-exhaustive patterns in function F. Right. F of anything else. Nothing. Yes, this is... okay, now we have 202. We're supposed to be getting 208. Okay, let's see here. What is wrong here? So it says we covered addresses 26, 27, 58, 59. Yeah, that was the first one, right? And then it's supposed to cover 16, 17, 18, 19, 24, 25, 26, 27. Is it because I forgot to reverse? Nope, we already reversed. Wow. Well, you can compile Haskell to JavaScript, right? So... you know... you can just do what you want. Let me see. Now we're gonna be doing debug tracing! Whoop whoop! We don't use any of these. Import debug dot trace. Checkmate Simon. Why would you checkmate Simon, huh? Trace show id. Oh my god. Address set. No. Woo. LeFou. Trace show id. Let's see. Let's see what's doing. Yes. There were trolls all along. Okay, so it's working. But only for one of them. So it's working for this one. Why is it only generating 58 to 59? So address set. So something wrong with our address set function here. Let's see. Mask to addresses. Okay, now let's look at the let's look at the trace show ID of xlooks. Yeah, you're supposed to meme on Twitch, right? You know, cause I wish I, you know, it's gonna sound bad, but you know, I've tried to be like, every time it doesn't work, I do like F in chat, but then it usually works. But you guys, you have to be spamming the memes, kappa, all that stuff. Okay, so the xlooks work. Yes. You know what? If you're gonna be recursing, make sure you actually recurse. IS. Yeah, so there's gonna be where so far prime equals Okay, let's see. Upd. So that's gonna be upd xloc is. So for prime. Does it work? Yes! We get 208. And look, we get all the addresses. And yeah, let's see. Let's see how bad is it? Measure, command, expression. Can you imagine if I was in Linux right now? I could just not write these things. 51 milliseconds. See, now it's like, oh, you don't need these. Now that's true, but like here. Is it gonna work? No. Why are you telling me? Ugh. What is it? Oh, okay. Like, yes, I can do this, but sorry, I don't want this blue line here. And here it's complaining that it's just function. It's complaining that is nothing. Okay, see, now I'll say is nothing. Okay, that is in data maybe. Okay, but in base, pogs, VSL2. That's Windows subsystem on Linux 2, and the absolute mad lads over at Microsoft. They just have an actual Windows kernel, a Linux kernel running on a Hyper-V. Like they're virtualizing an actual Linux machine on your Windows machine. And then you just like SSH into it. And then like VS Code will be running on my Windows machine, but like it has a remote connection to the VSL machine. So it's super fast. And you get all the goodies of actual Linux, you know, because it's in the actual kernel. So like even weird programs that use like kernel functions, they work. And they are going to add GPU support soon. Why I'm not using it at the moment, like I've said before, you need to update to Windows 2004 or Windows 10 version 2004. But I am not allowed by my organization to do that, so I can't do it. Yeah, I know. I would do it, but it doesn't work. So once I'm allowed to update this to the latest and greatest Windows, I can finally go back to that. But you know, I don't have. I didn't bring my desktop all the way over here. Can I get an F in chat? Okay, so I think, what I'm thinking is that this is not too bad. We're just taking set unions and stuff. And then we're only adding things if we need to. We're not like building the entire map or running the entire program. So this is kind of like the program analysis way of doing it. Oscar Allen, they're the only one actually... They're actually like the other ones are just on, you know, Twitch to watch this content, but he's the Twitcher, you know. He's he knows what it's about. Okay, can I? So this works on the input, and the time to beat is 220 milliseconds. Let's see. Let's remove these addresses. I mean, they won't be used if we're not actually using it, but it's gonna be fine. Wow. Hey, you can use my new emoji. It got accepted this weekend. Are you all ready? Are you ready? Alright, this is the new emoji. If you don't understand something in Haskell, just go Tritlo, And it has the Haskell logo with a on it. I stole it from SuriHack. Well, like, I stole it from the... I borrowed it from the SuriHack Discord server. It is so good. I just want you to go forth on Twitch. And like, every programming thing, just like, why aren't you using Haskell? I love it. I love it. So this is gonna be fast. This is gonna be fast. Now let's remove these trace show IDs. This here, however, is not gonna be fast. Fold L compose over something. Let's see how it does on the input, and if it's taking so long that we can't wait, then we will stop. So where's the last debug trace? Trace show ID. It's here. Some actual drops in these songs. It's good. Okay, and then I don't actually use this. Oh, thanks for the follow. You know, I appreciate all follows. They are nice. Yeah, Monad tutorials. They are yeah, there's something. You know, the real Monad tutorial is always in the comments. No, the real Monad tutorial is to realize that monads are just... What? They're just an endofunctor in the... They're an endofunctor, they're a monoid in the category of endofunctors, you know? But I think, you know, if you so like when I figured out monads, if I can say I've done that, was when I realized that there's nothing to figure out. You just use them. Exactly. You literally just use them and you read the compiler errors. And if you fix those errors, the monad works. So just do that. Okay, so this is gonna... We're gonna rock it. We're gonna rock 'em, sock 'em. Are you ready? This is gonna take a bit longer. Ooh. I think there's some debug trace there. Can I get an F in chat? Because my editor just froze. Oof. What did I do wrong? Are you getting frame drops and stuff now? Because am I just not broadcasting anything anymore? Ooh. God damn. Video's still good. Good stuff. Okay, that was fun. But this is why you need to test. Day 14. Let's run it again. Let's run it back. On the test input, there's some... What is this from list? Oh, is it because I'm... Oh my god. But you see, it finished. You wouldn't have started printing that list if it hadn't finished, right? So it didn't take too long. Wow! 25 milliseconds on the test input. I got impressed for a second there. But I was too impressed. So we got the list of literally every address. Okay, 200 milliseconds. Is this correct? Let's see. That's not the right answer. Oof. Can I get an F in chat? Damn it. Oh my god. Wow. So we reverse the blocks. And then we only add the ones that... Let's make sure we actually reverse the blocks. That is a bummer, yeah. Seems like a way to go, right? So this is the mask. And then it says 6113, 674, 637. And let's look at our input. 6637 5249. Yeah, this is we did reverse it. It compiles, it works, yeah. I'm gonna take a 1 minute break. I just need to get over this. You know, it's too much. Give me a sec. I know what the error is. I know what it is. So it applies memory operations, and the thing that we're doing wrong. So we only update the values that are going to be updated. But what we did wrong is that we didn't flip the memory operations within the blocks, right? So if you get an overlap later in the block from something, that's what we didn't flip. So here we have the updx logs. So we need to take care. We need to fix it. We need to make sure that it does it correctly. So this is mask to addresses. So add an update. So are we reverse? I think that's the issue. Let's see. This is not the same number as before, right? We said something like this. I think it's gonna be this. Alright! We were missing one more reverse. Damn it. Okay, that was... yeah, alright. We did it. The thing is that because we reversed the entire thing, right? So we did per block. But we forgot overlapping addresses within blocks. That would always resolve to the last one. What time did I get? 127 milliseconds. Just the program. Yeah, around 120. This is actually faster for some reason than the one where we didn't reverse him. I don't know why. What if can we optimize it a bit? Can we just say in 64 here? Total val added, and then this is gonna take in I think that's the issue. Slightly, well, okay, that didn't change much. Yeah, we can do this fix. So we did it. It worked. It took you, what, 0.8 seconds? It took me, you said 220 milliseconds, right? Something like that. So you did it in 0.08 seconds. That's 80 milliseconds, right, Timmy? That's pretty good. We got it in 120, but yeah. I think maybe, you know, if you do it with data.map and you use like the lazy map, it won't do anything unless until you actually sum the elements in the end. And then like all the lazy updates will just have been, you know, like, oh, I won't update it here, I will just have updated it with the exact value that it ended up being with. And like we're essentially calculating all that already. Let me see. Let me see. Data.set. Data.set Haskell. Yeah, I'm a bit disappointed in that it's not as fast, I have to admit. Boom, 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 boom. We could we could try something. Let's see, invert. Yeah. Oops. Yeah, you see I have 1909, but I need 2004 for it to work. Yeah, I think that's gonna be it. I don't think we can... I mean, there's not so many... There's not so much we can fix here, right? This is all just gonna take a lot of time. Let's see, maybe if we can do the set bit and that stuff. That bit. But, yeah. So let's see. So I'm thinking about this. Flip set bit. Just a. I'm thinking if we could just like generate the one. Yeah. So you need to like update the VSL some way. You like need to, I think you kind of need to remove the old VSL and then update the VSL to make it work. Let's see. Yeah. Fold L prime. That's not. That doesn't matter, right? $110 milliseconds sometimes. I think it's also to me that you're like not running OBS and everything at the same time. That might be it. I think it's hard. So I think we have like the same order. I was just wishing that this would be a bit faster, because we do avoid doing a lot of computations. But then again, it means that I'm doing so many set operations, which don't really matter. Like, because I like figure out exactly which ones I'm going to update, and then we add the value with that also. But I think there is a way to do this. Using some clever bit tricks, by saying, okay, what is X? So if you want both values, you add 64 to it, and then you if it's setting that bit, so you could flip it. There is like definitely some clever integer bit binary tricks you could use here, but we're just not seeing it. Let's see, fold L. So base is this. So fold L, id map maybe. We're gonna be applying that all the time. So let's do here. Let's apply this to 0 bits. What? And bid is gonna be, so base applied to 0 bits, and then num to work with, that's going to be That may be F. So base is gonna be a function from int 64 to int 64. And bid, and then this should be number to work with is I64. I think it's, and then we do XOR with the bid. We still get the same. Then we set all the bits to 1. This is still wrong answer, right? Be out here. And actually, this is all. Yeah, I mean, we're always around that mark, right? Like 120-ish. Yeah, I was just trying. I tried to change it, see if it like helped, but it didn't change anything. So the fold L1 is strict, and like we're going to need we need the results of everything. So like yeah. But this here thing is always going to be exponential, right? Or like this is going to take a lot of work to calculate this. So yeah, I don't think we can boost the I mean, it's definitely like I don't think we can do this in any faster runtime. You know, not without figuring out how the coverings work, without doing set operations. That's just too much, right? Yeah, I'm gonna go offline now for like an hour, and then I'll come back, and I hope to see you all then.